Okay, let's dive right in. Welcome, everyone, to today's explainer, where we are absolutely decoding the examiner's blueprint for Cambridge computer science. Now, think of me as your astronomer today. But listen, instead of looking up at the night sky to navigate by the actual stars, we are going to navigate by the key command words in your exam paper. We are going to chart your exact course to top marks. To truly understand the stakes here, I want you to consider a real Cambridge computer science past paper question. And we're talking across the board here. The rigorous standards of the 9618 and 9713 syllabuses, right down to the foundational concepts you see in 0417, 0478, 0983, 0984, and 2210. The principles apply universally. So take a look at the two archetypal students we see fail every single year. Let's call them Alex and Sam. Now, Alex is what we call the overloader. Alex looks at a 6-mark question about array data and linear searches, totally panics, and just dumps every single raw computer science fact onto the page. There is zero analysis, literally just a massive, unreadable wall of text. Then, on the other hand, there's Sam. Sam is the rusher. Sam sees the word array, freaks out about the clock ticking down, scribbles a quick loop, completely misses the specific command word requirements, and entirely forgets to verify the logic. Both of these students studied incredibly hard, but both of them are losing massive points, leaving bleeding red pen marks all over their papers. Why is that happening? Well, let's find out. The single most crucial number you absolutely need to know going into this exam is 15. That's right, processing array data and linear search algorithms account for approximately 15% of your total paper 2 marks. Just think about that for a second. That is a massive chunk of your final grade sitting in just one specific topical area. It's make or break. When our friends Alex and Sam hit this 15% wall, they completely crumbled. And it's because they lacked a systematic approach. See, Alex wrote a perfect textbook definition of a linear search. He explained that it checks every item sequentially from index 0 all the way to the end of the array. Is that true? Yes, absolutely. Did it answer the analytical part of the specific question asked? No, not at all. So 0 marks for the final evaluation. Meanwhile, Sam rushed and wrote a really basic for loop to search an array, but completely forgot that a linear search should optimally stop the exact moment the item is found. You do that using a Boolean flag and a while loop, not a for loop. Because of that, Sam lost those crucial method marks. This 15% challenge is exactly what we are going to conquer today, step by step. Because algorithmic thinking requires strict step-by-step decomposition, we are going to follow this exact structured logic for today's explainer. First, the 15% exam challenge, then mastering the theoretical foundations, the method mark strategy, the top examiner warnings, and finally, critical analysis and evaluation. Okay, section 1, the 15% exam challenge. Let's really unpack the core concepts here and talk about why the stakes are so high. So to understand how to actually get those top-tier marks, you first have to understand how the assessment objectives are structured. Cambridge isn't just testing your ability to blindly memorize pseudocode. They are testing your ability to logically deconstruct a scenario, apply a framework, and critically evaluate the outcome. Which brings us to a really critical point raised by senior examiners. Why do students find interpreting complex binary representations so incredibly hard? Well, when you store data in an array, especially down at the system level, you are often dealing with raw binary representations, memory addresses, and very distinct data types. Students struggle here simply because they lack a structural framework for their written answers. This is where I need to introduce you to an absolute game changer. It's called the PEEL framework: point, evidence, explanation, link. Top students use PEEL to structure their computer science answers flawlessly. You make your point about the binary representation or the array index. You provide evidence extracted directly from the specific scenario given in the exam question. You provide a technical explanation of how the linear search processes that data. And finally, you link it right back to the core requirements of the command word. But listen, before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's keep building this system. Moving right along to section 2, mastering the theoretical foundations. Let's see how theory actually builds a path to top marks. Look, theory in computer science isn't just boring background noise. It is literally the bedrock of your algorithmic thinking. If your theoretical architecture, meaning of precise definitions and causal relationships, is weak, your pseudocode will totally collapse under the pressure of a complex exam scenario. Examiners strongly prioritize candidates who show genuine analytical depth and cross-topic connections over those who just provide a superficial breadth of knowledge. Let's do a quick comparison to show you what I mean. Alex writes, an array is a data struct, a linear search goes through it, it takes ON time, arrays have indexes. Okay, that is the definition of superficial breadth. It's just a list of facts. Now let's look at Sam, who has learned our new Peel framework. Sam writes, a linear search is highly appropriate for the specific unsorted array of temperature data because the data is continuously appended without sorting. A sequential item-by-item check starting from index 1 to n is required, ensuring that the system can locate anomalous temperature spikes even in unstructured historical logs. Wow, right? Look at that difference. Sam achieved analytical depth by connecting the algorithm directly to the specific use case context. Making those cross-topic connections, like linking data structures to system requirements, acts like a massive multiplier for your marks. Section 3. The method mark strategy. Knowing what the examiners want is only half the battle. Now let's explore how you are awarded marks for the actual process itself. This is where the magic happens. This is where we take those bleeding red pen marks from our archetypal students and completely transform them into green check marks. Whenever you tackle an algorithmic problem, strictly follow this standardized sequence. Deconstruct, extract, select, execute, and present. This 5-step sequence is your computer science success blueprint. Let's actually do a live rewrite of a common question in our heads. Imagine you need to write pseudocode to find a specific user ID in an array of 100 users. Step 1. Identify key elements. Okay, we have an array, it has 100 elements, and we have a target user ID. Step 2. Apply relevant principles. We know we need a linear search, but to optimize it, we need a Boolean flag. Step 3. Execute analysis with clear working. This is where you write your actual code. You'd write, declare found Boolean. Next line, found occurs less than false. Then, declare index integer, and index occurs less than 1. Step 4. Verify results. You have to ask yourself, what happens if the ID is at index 100? Or what if it's not there at all? You trace it using a while loop. While index less than or equal to 100 and found equals false. Step 5. Present an appropriate format. Use correct syntax, capitalization, and proper indentation. When you lay your answer out showing this precise step-by-step working, even if you make a tiny syntax error at the very end, the examiner sees your procedural framework. You grab 4 out of 5 marks just for the method. You are literally proving your algorithmic decomposition skills on the page. Now stop scrolling. Subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's jump into Section 4, Top 3 Examiner Warnings. Because even with a solid framework, you absolutely need to know where others fail. Let's treat this like an interactive workshop. We are going to look at the specific pitfalls that destroy grade boundaries, pulled directly from principal examiner reports. You have to avoid these 3 major traps. First up, confusing cause and effect. Think about the execution times of a linear search across arrays of different sizes. As the array size doubles, the worst-case execution time roughly doubles. If you miss that, you are confusing cause and effect. The cause is the sequential nature of the algorithm. The effect is the linear growth in processing time. Second, let's play Find the Flaw. I'm going to read a sentence and I want you to spot the error. Ready? To find the rogue data, I will use a linear search to check every index from 1 to 100. If the data is found, it prints error and continues to check the rest of the array just in case. Did you catch it? The massive flaw is that it continues to check the rest of the array. That completely violates the principle of algorithmic efficiency. A properly optimized linear search should flag that it found the item and instantly terminate the loop. Furthermore, what if the array only has 50 elements populated out of the 100? This is where context matters immensely, which brings us to our final warning. Always be specific to the context. I really want to pause here because principal examiner reports reveal that candidates consistently confuse key terminology. Listen to me. Always define your terms first. If you were asked to define a boundary condition in the context of an array linear search, your answer should look something like this. A boundary condition refers to the extreme limits of an array's index, such as the very first element at index 0 or 1, or the final element at index n. In a linear search, testing these boundaries ensures the algorithm does not cause an out-of-bounds runtime error when searching for an item that might be at the very end or completely missing. Therefore, correctly defining the loop condition to stop exactly at the array's upper bound is absolutely critical for system stability. If you can write a paragraph like that, you are thinking exactly like a senior examiner, and the marks will just flow. Finally, we've arrived at Section 5, Critical Analysis and Evaluation. Let's look at how to reach the absolute top tier of scoring. Top scoring candidates constantly use this specific loop, the deconstruct, solve, evaluate loop, to identify given information, solve systematically, check for reasonableness, and make justified recommendations. We are locking in all these techniques today so that you have an impenetrable armor of exam strategy. If you want to guarantee top marks, you must follow these 3 golden rules based on this loop. Rule number 1, command word decoding. You must look at the stars to navigate. If the command word says evaluate, you cannot just describe. Describe means stating characteristics. Evaluate means analyzing trade-offs, strengths, and limitations. Rule number 2, the Peel framework application. As we discussed, point, evidence, explanation, link. Never, ever leave a point unexplained or unlinked to the specific scenario context. Rule number 3, the time management matrix. You must allocate your exam time strictly based on the mark allocation. Let's say you have a 6-mark algorithmic question. That gets roughly 8 to 9 minutes of your time. You spend 2 minutes deconstructing the problem, 5 minutes writing the solution, and 2 minutes evaluating and verifying your code. Strict discipline is key. When analyzing trade-offs or comparing multiple algorithmic solutions, your comparative analysis must include these specific elements to demonstrate true evaluative thinking. If an exam question asks you to compare a linear search with another algorithm, like a binary search, you must explicitly use comparative connectives, words like whereas, conversely, or in contrast. For example, you would write, a linear search is highly efficient for small, unsorted arrays as it requires no prior data organization. Conversely, a binary search is significantly faster for large datasets, but only if the prerequisite of sorting the array has already been met. Do you notice the clear evidence and the relative importance drawn in that conclusion? That is exactly how you max out the evaluation marks. This entire methodology, securing the method marks, applying the Peel framework, and extracting the exact context, it entirely changes the game. So, as you review your notes from today's session, I want you to ask yourself, how will you rewrite your next linear search algorithm to prove your analytical depth? Will you be the student who just lists basic facts or the strategist who builds an unbreakable evaluative system? The marks are right there waiting for you to claim them. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but that only happens if they practice consistently with our weekly videos. So here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're currently facing. Our team responds to every single comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. I'll see you in the next explainer.